Okay, so this is 17.3 acid-base titrations, and we're going to break this up into a couple of different parts here. So what we're going to do is we're going to look at acid-base titration. Now, when you take the first semester of general chemistry, you generally do a acid-base titration. But now what we're going to do is we're going to actually do a titration curve. So the idea here is that we're going to take a burette, right? And then underneath that we'll have either a flask or a beaker, some type of container. Here we'll make it a coffee cup. Okay? And for this particular titration, what we're going to do is we're going to put a solution of hydrochloric acid. Okay? We're going to have 0.1 molar hydrochloric acid. Of course, it's dissolved in water. And we're going to have a volume of 25 milliliters. Okay? And then what we're going to do is we're going to put in a pH probe, a device that can measure the pH. Okay, very nice device. These devices are commercially available. Okay, so we have a pH probe inside there, and then in the burette, we're going to fill that up with sodium hydroxide. And for this example, we'll make the numbers easy. We'll make it 0.100 molar. Okay, same concentrations of each of them. And I'm going to show you a few little calculations. So the first thing we're going to do is we're going to calculate the pH of the HCl. So I'm going to make a little table here. Volume of sodium hydroxide added. Okay. And we're going to keep those numbers up here because we're going to do a little graph with these numbers. Okay. So let's measure, or let's calculate the pH of the HCl before we've added any sodium hydroxide. So the amount of NaOH that we've added is 0. And let's make sure that we know this is in the units of milliliters. Milliliters. Okay. All right. So what's the pH of 0.1 molar HCl? Well, that's pretty straightforward, right? Because it's a strong acid. So the concentration, 0.1 molar, we can use that in the calculation of pH. Its pH would be the negative log of 0.100 molar. And so that would be 1.00. That's easy enough. Right? Strong acid. If it was a weak acid, it'd be a little bit more complicated. We have to do an equilibrium calculation. But strong acids is pretty straightforward. Okay? So now, let's do a little bit of the titration. So in the next calculation, we're going to add 10 milliliters of sodium hydroxide solution. So we're going to open up a valve in the burette and add sodium hydroxide, and the volume is going to go up 10 milliliters. Okay? So the volume we're adding, this is not the total volume, but this is the volume that we added. Okay? And we're going to calculate the pH. So let me show that over here on the right. Here's how you do the calculation. You take the first reactant, HCl, combine that with the second reactant, NaOH, and it's an acid-base reaction, right? So you get H2O and NaCl, right? Double displacement reaction. Now what I'm going to do is I'm going to calculate how many millimoles there are of each reactant that we're mixing together. So I'll do that right here. Millimoles of HCl. Now, the way you do this is you take the volume, which is in milliliters, and you multiply that by the molarity. Okay, so the volume of HCl is 25.00. That's down here, right? And the molarity is 0.100 molar. So what does that give you? That gives you 2.5 millimoles. Okay, right? The liters cancel, and you have millimoles. So we just call those millimoles. So I'm going to write that down up here. I'm going to write this as 2.5 millimoles. And then I'm going to do the same thing with the sodium hydroxide. Millimoles NaOH. So that would be the volume in milliliters. Now we've added 10 milliliters of NaOH. So 10 milliliters. And its molarity is up here, 0.100 again. And 10 times 0.1 is 1, so you get 1 millimole. Okay? Now, here's what happens. These two are reacting. The sodium hydroxide is reacting with the HCl in a 1-to-1 ratio, right? So every time that one HCl reacts, it reacts with one NaOH until one of them completely runs out. The one that runs out is the smaller one, the smaller amount, which is the sodium hydroxide, right? 1 millimole is less than 2.5. So the amount of these two reactants that reacts is 1 millimole. So this becomes 1.5 millimoles, and this becomes 0 millimoles. So this is all gone, right? There's no sodium hydroxide at the end of this reaction, at the end of adding 10 ml. But there is still HCl left over, 1.5 millimole. Now remember, HCl is a strong acid, right? So we can calculate the pH of a strong acid just by knowing its concentration. So now we calculate the concentration of what's called the excess HCl. Excess meaning what's left over after the reaction with NaOH. So it's the number of millimoles that we have left over divided by the volume. But the volume is now larger. It's no longer 25 ml. It's now 35, right? 25 plus 10. So we divide this by 35 ml. And look what happens to the millis. They're gone, and you have moles per liter or molarity, so you can do your calculation of pH. So 1.5 divided by 35 is 0.0429. 0.0429. That's HCl. So the pH, negative log of 0.0429. So let's come back over here. Negative log, so log negative 1.37. Still acidic, we still have excess HCl, so the pH is 1.37. And you would do any calculation of pH for this titration the same way as long as the number of millimoles of HCl is greater than the number of millimoles of NaOH. So in other words, if I had put 9 milliliters of NaOH, you would just put in for the NaOH 9 milliliters times 0.1 molar. Get your 0.9 millimoles. Subtract 0.9 millimoles from here, and you'd have 1.6 millimoles of HCl left over. So what I would recommend is you practice those. You could practice it by doing 5 milliliters of NaOH, 10 milliliters of NaOH, 15 milliliters of NaOH. I would recommend actually, just to begin with, pause the video, do this entire calculation as I did, and see if you get pH 1.37. Okay? Just pause it and do that and see if you get that value. If you can't get it, watch the video and see what you get. Okay. Now, in the second calculation or it's actually the third calculation I want to do here, I'm going to pick 25 milliliters. We're going to add instead of 10, so not another 25, but a total of 25 milliliters of NaOH. And we're going to calculate the pH. Now, I'm picking that number for a reason. And you'll see what the reason is once we get to that point. So it's the same idea, though. We're going to take HCl. We're going to react it with NaOH. We're going to get H2O and NaCl. Remember, you have the H plus, the Cl minus, Na plus, OH minus. The H plus goes with the OH minus for water, and the Na plus goes with the Cl minus for NaCl. Double displacement reaction. Now, the number of millimoles of HCl, we already calculated that in the previous problem. That's not different. The amount of HCl that we put in here is not any different. It's still 25 milliliters of 0.1 molar. So this is still 2.5 millimoles. So we're restarting the calculation here. What changes now is NaOH. For NaOH, remember, it's the volume in milliliters, so we're adding 25 milliliters. And then we're multiplying that by the molarity, which is up here, 0.100 moles per liter. And look what you get, 2.50 millimoles. I picked this particular volume, 25 ml, on purpose to show you that we're going to get the same number of millimoles for NaOH. Okay, here's what happens. These are stoichiometric amounts, meaning that we have the exact amount of each reactant to react completely with each other, with the other one. So we subtract 2.5 from both. And that gives us 0. And that gives us 0. And we now have an issue. The issue is, how do you calculate the pH of 0? You can't calculate the pH of 0. The logarithmic function is not defined for a concentration of 0, for a value of 0. So we have to figure out what's going to happen. So we'll get into the chemistry then. HCl in the first two problems was the excess reactant. So it determined what the pH was. Now HCl is gone. It's been used up. So has NaOH, however. So what we have to do is we have to look at the products. We have to ask ourselves, what would the pH of water be, and what would the pH of NaCl dissolved in water be? Well, NaCl has Na plus and Cl minus. This is the conjugate acid of NaOH. And what we said in chapter 16 is that the conjugate acid of a strong base has no effect on pH. So if you need to, go back to the chapter 16 videos on that. This is the conjugate base of HCl. It has no effect on pH. So that means this is 0, so it does not affect pH. This is 0, so it does not affect pH. And because these are conjugates of strong acids and bases, it has no effect on pH. So we're just left with water. What's the pH of pure water? It's 7, right? Pure water at 25 degrees C has, at least theoretically, a pH of 7.00. So this is 7, and this occurs at the equivalence point. That's what's special about this particular value, this particular calculation, is that the millimoles of each reactant are equal. So the millimoles of HCl are equal to the millimoles of NaOH. That's called the equivalence point. And so I'm going to give you an important conclusion out of this, an important result. For a strong acid, strong base, titration, the pH at the equivalence point is equal to 7. Now the requirement is that it be a strong acid and a strong base. It cannot be a strong acid with a weak base, or a weak acid with a strong base, or a weak base with a weak acid. It has to be a strong acid with a strong base, because the products are water and a salt, and the salt does not have any effect on the pH. So for that reason, at the equivalence point, it would be 7. Remember, the equivalence point is when the number of millimoles of each reactant are equal to each other. For this particular titration, that occurs when the volume of sodium hydroxide is 7. I'm sorry, when the volume of sodium hydroxide is 25. Okay? So let me now, I'm going to try not to erase that table that we worked so hard to get. I'm going to show you one more value. And that is the case where we add not 25, but 35. So now we're going to add 35 milliliters of NaOH solution. Remember, it's dissolved in water, so it's not pure NaOH, it's NaOH dissolved in water. Okay? Now, let's do the same calculation. HCl, NaOH, H2O, NaCl. Okay? Again, this was 2.5 millimoles. We're not changing that. But now, here's what happens. Now it's 35 milliliters of NaOH, and the concentration is 0.1 molar, so 35 times 0.1 is 3.5 millimoles. So this calculation, the millimoles of NaOH, is greater than HCl. HCl is now the limiting reactant. That means it will be 0 at the end of the reaction, but we'll still have excess NaOH. So we subtract the smaller. Let me actually make a little more room over here. So minus 2.50, minus 2.50, 1.00, 0.00. So this is 0. Now we have a strong base, excess, strong base. Okay? So this is 35 ml. So we know it's going to be basic. That's one important point to make. It will be a basic solution because we have excess strong base after the reaction is complete. So what do? So now we calculate the pH of a strong base. Again, to calculate the pH of a strong base, all you need to know is what its concentration is, calculate the pOH, and then take 14 minus that. Okay, so let's figure out the concentration of sodium hydroxide that is in excess. 1 millimole. And now we just have to be careful. The volume was 25 plus 35. That's 60 milliliters. Millis cancel, so it's 1 over 60 in moles per liter. And there you go, 0.0167. Sodium hydroxide, strong base, pOH, negative log of that value. take the log, change the sign, 1.78. Be careful. This is not the pH. It's the POH. So the pH is 14 minus that. It's basic, right? It's got to be basic. It's a strong base. It's going to be above 7. So take a look at what has happened. When we started off with the strong acid, pH was very low, strong acid. We added a little bit of the base. It only went up a tiny bit. Then we went to the equivalence point. It became pH 7, which is neutral. And then once we added some excess sodium hydroxide, it became very basic. There you go. Redo all 4 of those calculations on your own. I highly recommend you get good at doing that. Now, what I'm going to do is I'm going to show these values graphically, and I'm going to add some fake points in, which won't be exactly right, but that's okay. Oops, let me go ahead and put in that there. Okay, so what I'm going to do is I'm going to show you a titration curve. The titration curve is a way of representing this data. It's kind of a cool way to represent the data. So on the y-axis, we're going to show pH. And then on the x-axis, we're going to show volume of base added. And I'm going to write base because it could be sodium hydroxide or it could be any base. And this will be in milliliters. So we'll make our scales here. 0, we went all the way to 35, right? So let me do 10. Try to make these pretty evenly spaced. It's not perfect, but there's 50. We didn't go up to 50, but I'll extrapolate a little bit just to show you. pH, it's probably convenient to start at 0. We could start at 1. I mean, the first value is at 1, but I'll just put 0. And then we went all the way up above 12. So let me do this. Let me do 2, 4, 6, 8, 10, 12, 14. And I will put 7 in there because one of the values was 7 and that's neutral, so it's not a bad idea to put that in there. Okay, when we didn't add any sodium hydroxide, we had a pH of 1. So 0 gave us a pH of 1. So there's 1 point right there. I'll make the points big. The second one was 10 milliliters and it went up to 1.37. So on this curve, it looks about like that. It really only went up a tiny bit in terms of the scale here. Okay. But then when we got to the equivalence point, which is at 25, it went all the way up to 7. So I'm going to try to do that as effectively as I can. I guess about right there, right? All the way up to 7. It's a big jump. And then when we went up to 35, it was all the way above 12, 12.2. So 35, 12.2. Okay. So those are just 4 points, but I want to show you what the general curve looks like, approximately. It rises very slowly, and then it actually, let me even just redo that a little bit. It rises very slowly, and then jumps, it leaps up, almost vertical, and then it comes out like that. And it will, it'll have an asymptote at 13, at pH 13, because the highest concentration that it could ever be would be 0.1 molar because the sodium hydroxide was 0.1 molar. So this is called an acid-base titration curve of a strong acid and strong base. It generally looks something like this. This is sometimes referred to as a sigmoidal shape. Or a S-shaped curve. It is a response curve and is commonly seen for pH curves, for pH titration curves. There's other types of There's other types of reactions that give curves similar to this as well, which we won't discuss. Okay. Now, the equivalence point is right here in the center. This is the point on the curve. This is called the equivalence point. And this is the case where the millimoles of the HCl, the analyte it's called, is equal to the millimoles of the sodium hydroxide, which is called a titrant. At that point, for this particular titration, a strong acid and a strong base, the pH would be 7. And that equivalence point occurred when we added 25 milliliters of the base. Okay? So gradual, very sharp increase followed by a leveling off, tending towards, if we added enough sodium hydroxide and diluted the solution, its concentration would eventually become 0.1. That would level off at pH 13. Okay? So acid-base titrations, there's your curve. This is part 1. In part 2, we'll look at a separate titration.